Hi, dear students. I welcome you all to this lecture series on theory of semigroups with course code MMTE 405. In this lecture series, we try to explain why these semigroups are very important, why we study semigroups. So we first try to answer this question: why we study semigroups? Why we study semigroups, or why semigroups are important, or why semigroups are important in categorical sense. In categorical sense. In fact, it's more important than groups in this sense. So, in order to explain this this idea why it's important in this in category, I would like to first introduce category. So let me introduce to you what do we mean by a category. So in this regard, I will first take an example of a category. So that's very important. Then we formally define category. So first I will explain this concept with the help of an example. Okay, concept of category. So let's take this triplet O, home and I. While O, it's a collection of all sets, and for any two sets, home of A, comma B denotes the collection of all mappings between the sets A and B. And for any set A in this collection OIA will denote the identity map on A. That's XIA is equal to X for all X in A. So what's this O? O is the collection of all sets. All sets. And for any two sets, home of A, comma B. What's home of A, comma B? It denotes the collection of all sets. Collection of all mappings, or you can say functions. Collection of all mappings between the sets A and B. Now I explain I. This I stands for actually identity of this triplet. For any set A, IA denotes the identity, denotes the identity. So let me write first here this. It belongs to actually home of A, comma A. So it's a map between A, comma A. Denotes the identity on A, which is defined by XIA is equal to X for all X belongs to A. So one more thing here I want to mention, that I will always write element on the left hand side of the map throughout this lecture series without further mentioning it. So this is the identity map, okay? And fourth, that's very important here, that's a composition of mappings. So for there is a composition between the mappings for any two mappings. F belongs to home of A, comma B, that's the mapping from A to B, and G belongs to home of B, comma C, that is F belongs to A to B, and that's F is a map from A to B, and G is a map from B to C. Then we can define a new map from A to C. That's called the composition of these two mappings. Now let's define this. Define FG from A to C by XFG. I always write element on left hand side. It's equal to X F. First I apply F on this element, then I apply G on this element. So it's the composition is called the composition is called the composition of F and G. Composition of F and G. Then we can we know that this composition it's associative, and if I apply the identity map to any map F, this F will never change. Okay, so let me write it here. Then this composition is associative. That is if F is a map from A to B, D is a map from B to C, and H is a map from C to D, then you can easily verify this. Then FGH is same as FGH. This is always true. That's associative. And second property of this composition is this IAXN identity. Yeah? Second property, and also for any set A, for any set this or you can say for any map, not for any set, for any map, for any map F from A to B, IA composition F, it's same as F, and it is same as F composition IB, where IB is the identity map on B. It's a map from B to B, and IA is a map from A to A. So this can be easily verified. And the last property is that the home sets are the home sets, the home AB sets are pairwise disjoint. So by pairwise disjoint we mean that if I take any two pairs of sets, two distinct pairs of sets, then home of one pair is disjoint from the, because home is actually the collection of sets mapping, so it's a set actually. That's for any two pairs of distinct sets AB and say CD. Let's take another pair CD. They are distinct means that means either A is not equal to C or B is not equal to D. Then this home of AB is disjoint from home of CD. This intersection is the empty set phi. So this can be this is simple, because since either A is not equal to C or B is not equal to D. So if I take any map here, that map cannot be here, because the domain of that map is A and the codomain is B. But here the domain is C and codomain is D. But for the equal maps, domain and codomain should be equal. And here, either these domains are not equal or codomains are not equal. So that means these two sets are actually disjoint, home sets. So any triplet having these three, this is a particular example of a triplet. Any triplet having these three properties, having these properties which I have already explained in this example, is called a category. So let me define this category. So let's define now category formally here. So what do we mean by category? So category, it's a triplet actually. A category is a triplet, like in this example, which we call the category of sets, because in that category, the first the collection O is the collection of sets, and home is the collection of mappings between the sets, and that category is called the category of sets. So we generally define this category. A category is a triplet. Is a triplet C which equal to O, home and I. And in this case, O is not in general the class of sets, home is not the class of mapping, I is not those identities which are in mapping, but it's a very general concept. O may be any set, home may be anything here. But if this triplet has the following properties, then this triplet is called a category. So it's consisting first a class O. It's a class O whose members are called, the members of O are called C objects, whose members are called, whose members are called C objects. C objects. So that means in previous examples the sets are C objects, because in that example O is a collection of sets. So that means the members of O are their C objects, whose members are called C objects. And second property, for each pair AB of C objects. And in previous example, this pair is the pair of sets there. It was the pair of sets there. So for each pair AB of C objects means the members of O. C objects as set home of AB, and in the previous example it was the collection of all mappings between the sets A and B. So here this home of AB, it is the this we call the collection of morphism, whose members are called C morphisms. Whose members are called C morphisms. Whose members are called C morphisms. Whose members are called C morphisms from A to B. Whose members are called C morphisms from A to B, and the member F belongs to home of A comma B, can be written as or can be expressed as F from A to B. We use the same notation as we have this notation for the function F, but in general it's not the function. So whenever F belongs to home of A comma B, we write it as F from A to B, or we can write it as F is an arrow from A to B. In case of functions, in case of previous example, it was a function from A to B, but in general we say it's an arrow from A to B in category. So for any two pairs, for any pair of C objects where A comma B, they are the members of O, and the members of O are called C objects. So they are C objects, it's a pair of C objects. A home set, which whose members are called, we call these members morphisms from A to B. In the previous example, the members are the functions from A to B. So therefore in that case the functions are morphisms. Okay. And Then in previous example, we have composed two mappings, and here again we define the composition, but in general they are not the mappings. So you should keep this thing in mind, that in general those f's are not functions. And now third property, identity. For each C object A is a C object, means A belongs to a morphism. A morphism IA from A to A is there. That's called the identity. Actually here IA, it belongs to home of AA, because it's a morphism from A to A. Is called the C identity. Is called the C identity. C identity. So for any C objective we have C identity. So in other words, there is one correspondence between the class, that object class O, and the identities. So C identity. You can define this. And fourth property is a composition associates. There is a composition, as in case of the category of sets, there was composition of two mappings. If F is a map from A to B, G is a map from B to C, then we can compose these two mappings to generate a new map FG from A to C. So again, in general, in category we have a composition. We can associate we have a composition. A composition associates. It associates with each C morphisms. With each C morphism F from A to B, and each C morphism G from B to C. So if you take any C morphism, any two C morphism F from A to B and G from B to C, we have a composition here. We should have composition there. A C morphism. This composition is a C morphism. It's a C morphism FG from A to C, called the composition of F and G. Called the composition of F and G. So there should be an associated composition of any two morphisms. So we must have the composition FG there. That's called the composition of F and G. This composition is subject to the following conditions. Subject to the following conditions. As in case of the category of sets, the composition is associative. Its identity map acts as an identity. So same is here. This composition should be associative. So what's the first property of the composition? First property is composition is associative. Composition is associative. That is if F is a morphism from A to B, G is a morphism from B to C, and H is a morphism from C to D. In case of previous example, these are functions. Then FGH should be equal to FGH. And the second property of the composition is that C identities, that means for any object A, I can define identity on A, that's called C identity. So these C identities act as identities. They act as identities. like in case of functions, they act as identities with respect to the composition. With respect to the composition, that is if F is C-morphism from A to B, then we must have this composition of IA with F should be equal to F. It should act as an identity, and it should be equal to F composition. This F composition identity on B. So identity on B should act as an identity on the right hand side, and this should act as an identity on left hand side, because F is morphism from A to B actually. So this composition first should be well defined, and here it's well defined because I is morphism from A to A, F is morphism from A to C, A to P. So that means IA F is a morphism from A to B, which is equal to F. And the last property that we have seen in previous example, that the homes are pairwise disjoint. Here it should be true. Home sets should be pairwise disjoint. The set home are pairwise disjoint. Pairwise disjoint. That means if we take any two distinct pairs of objects, say A, B and C, D, then home of AB should be disjoint from home of CD. So these are the properties of category. So any triplet O, home, I is said to be a category if it satisfies these properties. Now we give some more examples of category, as we already explained in one example, that's called the category of sets. Now let's take the example of category of semigroups. So the category of sets is denoted by SET. SET denotes the category of sets. Category of sets. So in this category we have a triplet. So SET, it's a triplet. It's a triplet O, home, I. And by O is the collection of all sets, home is the collection of all mappings between the sets, I is the identities. And the semigroup category is denoted by SRP, and this is equal to O, home and I. It's this triplet where here in this case this O is the collection of all semigroups. It's not the collection of all sets here, it's the collection of semigroups only. And home is not the collection of all mappings, it is the collection of semigroup homomorphisms. So what do we mean by semigroup